what you see in this figure over here, the solution, the fixed points x star as a function of r, a stable and an unstable branch coming together, merging over here and disappearing, what we called a tangent bifurcation. And then the other was fx equal to rx minus x squared, where one had a couple of fixed points crossing x star as a function of r, and crossing at this point over here, where there is a transfer of stability from one branch to the other. So this is stable, x star equal to 0 stable for r less than 0, and then the other branch, other fixed point x star equal to r becoming stable. The third was this fx equal to rx minus x cubed plus minus. In one case we had this stability transfer from this branch over here to this branch over here, and the system has this symmetry, x going to minus x in this case, and then the image of that where it's still this, but if you have the plus sign, then that's what it looks like. No stable fixed points on this side over here for r greater than 0 and x star over here. So it's also a pitchfork, but reverse pitchfork. This is what one generally calls the forward pitchfork, and this the backward. So these were the three cases that we talked about, and also said that what we have these simple systems, the simple form of f of x is what is called the normal form for these bifurcations. In the vicinity of the bifurcation point, call it some r critical, x critical. So in each case there is a bifurcation point in the x star r plane, and the bifurcation always determined by the creation or annihilation of fixed points, change of stability. So accompanying a bifurcation, there's creation or annihilation of fixed points and or change of stability. Here it's all two fixed points remain, here the transcritical, two fixed points remaining, two fixed points, but the stability changes. In the other two cases, pitchfork and in one case there is annihilation, the merge and disappear, and in this case new fixed points are born, so there is change of stability also the question. So these are the things which characterize it, characterize the bifurcation. The two of them are structurally unstable, the ones which have 0 as a fixed point always. So the transcritical and the pitchfork, where 0 is always a fixed point, is very sensitive to a small perturbation that I give. And so they are not structurally stable, but the tangent bifurcation is structurally stable. Well, a point that we had made about this normal form was the point that if I add, so suppose x dot equal to rx minus x squared, that's the normal form for normal form, meaning what is the simplest differential equation in which you are going to see this behavior. The behavior is at the r star x star, r critical equal to 0, 0. It's in the vicinity of this that you see the bifurcation. And the point was that if I had further terms over here, rx minus x squared plus something into x cubed plus something, I could always find a transformation which would sort of, if I start with x cubed, there would be a transformation which would sort of push the correction. That is, I could define a y such that in terms of y, it would be ry minus y squared plus order y to the power 4. So this kind of pushing the correction in the vicinity of the origin to higher order, you start with a correction which is at a certain order, x to the power n, push it to x to the power n plus 1, sort of tells you that this indeed is the correct form to use for a transcritical bifurcation. Anything that you add over here is not going to be near the point where the bifurcation is occurring, is not going to substantially change things. Now, we can, to make that point, in a case where things can be explicitly solved, let's look at adding x cubed term and see what the structure of the transition is all about. So this is x dot equal to rx minus x squared minus x cubed. I have just added, I could have put a coefficient over here. Or let's do that. Minus some alpha x cubed, and the point is that this remains exactly solvable thing. So let's see what kind of an effect is this going to have on the bifurcation diagram, which is relevant for the transcritical thing. So this is exactly workable. So x equal to 0, x star equal to 0 remains one of the fixed points. The other fixed points are going to come from alpha x dot square, x star square plus x star minus r equal to 0. So x star is equal to minus 1 plus minus square root 1 plus 4 alpha r divided by 2. So alpha x squared. Yeah. So alpha x. So that's that. In the limit of alpha going to 0, as you can see, one of the roots is going to be minus 1, minus 1. it's minus 1 plus 1, which is 0. And then there is the question of minus 1 plus 1 is 0 over here, which is a problem because you have to look at the denominator, which is also going to 0. So now you have to go one step further over here. So when I take the plus sign over here, and you get this 0 in the numerator as alpha becomes small, is to be expanded one further order, and so this would be 1 plus 2 alpha r, and so this one of the roots as alpha r tends to 0, so alpha tending to 0, you are going to come up with the root which x star, one of the roots would be minus 1 over alpha, the other root would be r. So this is so alpha going to 0 is going to push one of the roots off to minus infinity, and the other root would be at r. So 0 and r, which were the things which matter when I looked at the normal form for the transcritical chaps, would once again be the relevant chaps if the alpha going to 0, the third fixed point would be pushed off way back to infinity. So it would be pushed off to minus infinity, but all right, now let's look at it. So this is for alpha going to 0. I know what happens. What happens if alpha is non-zero? So alpha positive, let's say. So alpha positive means that so let's keep alpha greater than 0, and I'm looking at one root x star, which is minus 1 minus square root of 1 plus 4 alpha r divided by 2 alpha, and the other, which is x star, equal to minus 1 plus square root of 1 plus 4 alpha r divided by 2 alpha. So if I try and plot up these two, so the idea is to plot your x star against r, and x star against r always gives you there is one fixed point which is x star equal to 0. That fixed point is stable for r less than 0, so that's never going to change. And now I have these two fixed points over here, and if r is going to become alpha is positive, so you have a range of r equal to minus 1 over these fixed points exist only if r is less, or rather r is greater than minus 1 over 4 alpha. So if you make r negative enough so that 4 alpha r becomes minus 1 or even more negative, you don't have real fixed points anymore. So at r equal to minus 1 over 4 alpha, so somewhere over here, these two fixed points have the value minus 1 over 2 alpha. So these are sitting over here. Then if I go to r equal to 0, if I come to r equal to 0, one of them is going to be minus 1 over alpha. So this is from minus 1 over alpha, and the other is going to be 0. So you have one branch which goes off like this, and the other branch this is the, worried about the asymptote, but that's square root of r. So here it is. That's what the thing is going to look like. X star equal to -1 minus this is going to start out from here and go off in this fashion for any non-zero alpha. For any non-zero alpha, the asymptotic behavior is square root of r. Similarly over here, it has to asymptote out to square root of r. But so this is what it looks like. So this is what it looks like, and this has become unstable over here. So now the stability of these fixed points, this is stable, this is unstable, so this part has got to be stable. And then, of course, I mean, if that part is stable, this part has also got to be stable, which is quite all right, which is this is unstable, and then this is stable. So there you are. If now this is the complete picture. So if this is the complete picture over here, and if I look at the vicinity of r equal to 0 and x star equal to 0, then this is exactly what we had over here. So in the vicinity of x star equal to 0, r equal to 0, which is where the transcritical bifurcation is occurring, this x cube perturbation which you have put in is not going to have any effect. So it's a question of not making alpha big or small. It's a question of making however big your alpha may be, there exists a r which is small enough so that in the vicinity of this point x star equal to 0, r equal to 0, I always have a transcritical bifurcation. So adding a x cubed to this rx minus x squared in the vicinity of the point x star equal to r equal to 0 leaves this as a transcritical bifurcation. So that's the point that one was trying to make when the other day we said that look, if I have an x cubed addition over here, I can always find a transformation in the vicinity of for small r small x, which would push the nonlinear, the x cubed, the addition term to even higher powers and make it smaller. So that, I mean, you look at this exact solution, which is possible for having this additional x cubed term, and you see what one means by it. All right, so that's the one other thing which I wanted to clarify, that these normal forms, the normal forms which one talks about are, you have to realize, are the simplest forms for these bifurcations, but valid in the vicinity of the bifurcation point. That is, far away. This line, the two straight lines that you had over here are no longer going to look like straight lines. So basically I had in a transcritical bifurcation two straight lines intersecting. If I go far away, the straight lines may become something else. As you see, they become over here, but the point is that in the vicinity of the bifurcation point, did I have two straight lines intersecting with each other? That's all right. So you can you can look at this in a from a slightly the same thing from another perspective, that I'm looking at x dot equal to f of r and x, and I know that there is a bifurcation, this fixed point, that there is a certain fixed point r0, x0. So R0, let's say R critical x0 is a fixed point. So imagine that I've found this fixed point over here. RCx0 is a fixed point, which means that FRCx0 is equal to 0. I want to know that if I look at all the fixed points, Frx equal to 0 gives all the fixed points. I want to focus on this particular one, which is RCx0, and I want to see what would be the, if I were to expand, how, knowing this particular fixed point over here, what can I say? So knowing this one particular fixed point, RCx0, what can one say about the other fixed points in its vicinity? So if I want to ask that, because that's what the bifurcation was all about. Bifurcations were, fixed points coming together. Every time I had a bifurcation, whether it was a tangent bifurcation or a transcritical or a pitchfork, at the bifurcation point, several fixed points came together. So it's fair to ask the question that if I know a particular fixed point RCx0 of this function f of r and x, what can I say about the other fixed points in the vicinity? All the fixed points would have to satisfy f of rx equal to 0. So basically, I want to look at the solution of frx equal to 0 in the vicinity of the point rcx0. Right? So this is the condition for finding all fixed points. I have found one, and I want to know what is the structure of fixed points around this point RCx0, and so I want to see, this gives me all of them, so I can ask the question, what does this f of rx equal to 0, what does the solution, all the possible solutions of this, what are they going to look like in the vicinity of this particular point RC and x0, which I know is a fixed point. So given, for example, over here, knowing that the origin is a fixed point r0, x0, what can I say about the other possible fixed points of rx minus or plus minus x cubed? So that's the issue. So if you ask that question, because that, as we saw, is the only relevant question near the bifurcation. I want to look at this neighborhood of the fixed point where the bifurcation is occurring. So I want to look at this RCx0, which I know is a fixed point, and now I want to ask the question that is there going to be a bifurcation around near that point? If there is going to be a bifurcation at that point, then there should be other fixed points lurking in the neighborhood, and finding all fixed points is through this equation over here. So I want to look at the solution of this equation in the neighborhood of this particular point. So you do a Taylor expansion, f rx0 equal to f rc x0 plus del f del x at 0, 0 meaning that at r equal to rc and x equal to x0. So this is So that's what a double Taylor expansion about this point is going to look like. So this is 0. So the first term is 0 by definition. So 0 is equal to del f del x 0 x minus x 0. So that's how it goes. Suppose del f del x is not 0, then you can easily write x is equal to x0 minus del f del r divided by del f del 0 . So if the first derivative is not going to be 0 over here, then you can, in this xr space, easily find out that the gradient exists. There is this linear expansion about r equal to rc, and nothing is going to happen. I mean, you are going to have a smooth solution, x of r near x0 is going to be a smooth function if del f del x0 is not equal to 0. So there is this technical stuff called the implicit function theorem, which would ensure that given this del f del x at 0 not equal to 0, that in the vicinity of x0, x of r is going to be a smooth function. So nothing much is going to happen, which is all right, because nothing happens unless del f del x is equal to 0. So for something to happen at this point, at the point x naught r0, so at rc x0, something happens only if del f del x at 0 is equal to 0, which when we first started out was the condition for for this growth rate vanishing. Del f del x at the origin was the question where this determined del f del x, remember, at this fixed point determines stability of fixed points. And so to be at if you are going to change stability, things have to be marginal, and the first thing that you want is that del f del x at the origin is going to be 0. So things become interesting only if del f del x at the origin, so condition to have a bifurcation, so that is a question of having a set of solutions which are going to come and merge at this point x RC x0 is going to be, you are certainly going to have, you definitely need del f del x at that point to be equal to 0. Now with that gone, you now come to the next step over here, that alright, if that is so, then what I'm going to have is that this L0 is going to look like, so this F, which is f of F0 equal to f of Rx, would now be looking like del f del R at 0, R minus Rc, plus half del to f del x squared at 0 x minus x0 squared. So x minus x0 squared. Now there are these other chaps as well. Now I can ignore them for the time being because the point is that it was x minus x0 which had gone off in the first instance. So I need to look, the primary situation would be, I already have R minus Rc term over here, and so if I want to look at what's happening to the x, the most natural thing is to keep first x minus x0 squared and see what happens. There would be other terms which are there and which would have important roles to play as we go ahead. But for this, I mean, first let's think of the simplest business, that del f del x vanish, so I keep the next term del to f del x squared, which is x minus x0 squared. This is going to immediately tell you that x minus, this gives you the other branches. It now tells you that you have this x minus x0 squared in the vicinity of this fixed point. The fixed x minus x0 squared is going to look like minus del f del R divided 2 times that del to f del x squared, this at the origin, this at the origin, that into R minus Rc. So this is what the vanishing of the fixed point condition for x of R, x star over R, is going to give you, if I truncate things at this order. And question is, do you now see which of these we are, if I stop things over here, which of these 3 bifurcations that I would be looking at? Tangent, right? So you are looking at the tangent bifurcation. So x0, Rc x0 in that case is the point for the tangent bifurcation over there. So it's x minus x0, the 2 branches that you see over there, and the condition obviously has to be that for this to, for R greater than, let's say you want x minus x0 to exist meaning to be real for R greater than Rc, and then you must have del f del R 0 divided by this del to f del x squared at 0. This has to be negative. So this quantity has to be negative for R greater than Rc. So if you you can just go ahead and fix values for this. What one typically does is set del f del R at 0 equal to 1, del to f del x squared at 0 equal to minus 2, And as soon as I do that, and with what I land up with is the situation that x dot is equal to r minus rc, set rc equal to 0, set x not equal to 0. This is r minus x. So these normal forms that, so what's the bottom line? Bottom line is that by looking at x dot equal to f of rx and looking at the behavior, suppose I know a particular fixed point, and if I want to look at the fixed point structure of x dot equal to f of rx in the vicinity of the fixed point that I know, I can ask the question whether there will be a bifurcation at that fixed point. That the condition for the bifurcation would have to be that this chap vanishes, which is exactly what every bifurcation, we know that there is some kind of a change in stability, so the del f del x determines the stability of the fixed point, and therefore it being 0 is the transition state. So that's what 0 at the origin is what you definitely require for bifurcation. If it didn't happen, then x0, this RCx0, the fixed point structure in the vicinity would simply be smooth. So your x equal to, which is a statement which you should verify when we did this additions to the x dot equal to fx, when we had this constant addition, and then for transcritical, and the behavior remains smooth at x equal to 0, at r equal to 0 and x equal to 0. So that's when the del f del x is obviously not 0, something which Taylor series expansion. If I go to the next order in the Taylor series expansion, the first thing I do is that I keep this term over here and keep these two chaps, the one which over here and the one over here. And you can see, alright, why did I in retrospect throw away the other chaps? If x dot equal to r minus x squared, where is the validity? Near the origin. My focus is near the origin over here. So this is, here is your x star and here is r. If I consider a region around the origin, where r mod r is less than epsilon, you give me a number, small number epsilon. I imagine a region which is r less than epsilon square and mod x star less than epsilon. So if I keep this, if I look in this neighborhood of the origin over here, then this is going to be of the, you are looking at a term of order epsilon square over here. You are looking at a term of the order of epsilon square over here. And then if I look at this term over here, I'm looking at epsilon squared times epsilon, which is epsilon cubed. And over here, I'm looking at a term which is of the order of epsilon 4. So I'm justified in dropping these two terms to study the bifurcation, study the normal form of this bifurcation, tangent bifurcation in the vicinity of r equal to 0, x star equal to 0. So so there exists this region around the origin over here, a region which is a rectangle whose width over here is epsilon and whose width over here is epsilon square and width over here is epsilon. In that region, your other terms that you have in that expansion over there are certainly going to be. Now, all right. Why epsilon and epsilon square, it's obviously by inspection, and the easiest is by inspection. If you want to, it does have proofs which are far more rigorous, but I mean, all right, I mean, this is pretty simple and for an argument of this kind to work. So you sort of look at it, and you know, if somebody asks you that is this normal form good, and then you say, aha, here is this rectangle of width epsilon times epsilon square, where it is good, where I can obviously see that the other terms are good. Very good. So that's, now you can easily see that I can play the game with the next chap around would require that. All right, let me put it as a question. Suppose I were to do look at the transcritical bifurcation. Which term would you like to set? Somebody else has to disappear. Yeah, I mean, somebody else has to disappear, and who would I like to remove in order to see a transcritical bifurcation? Del F del R, right? So out goes del F del R if you want to see transcritical bifurcation. So the next term which is going to come is so it's going to be x minus x naught square. All these quadratic terms over here, which you can cast as x dot. So those quadratic terms you can take and cast as a structure which looks like x dot equal to x squared minus r squared. That's the structure which you would be picking up. So it is x minus r into x plus r, and so it's your two fixed points. If I so one at plus r, another at minus r. These are your two fixed points over here. Stability determined by 2x star. So f of x equal to 2x star. So this is 2x star, which is 2r in one case and minus 2r in the other case. And there is exchange of stability as r becomes. And x minus r into x plus r does have this form of intersecting straight lines. So that's what the geometry is. X what you want near a transcritical bifurcation, basically two intersecting straight lines, and x minus r into x plus r does have this structure that it's two intersecting straight lines over here. So two intersecting straight lines, look at it as fixed point and look at the stability. There would be this inversion of stability over there. So that's your transcritical bifurcation. And similarly, to get the pitchfork, you obviously have to go to one higher degree, have to go to the next door, keep the cubic. Somebody else has to vanish. This would have to vanish. The cubic would have to come, and so on and so forth. So that's so all these things which we have talked about, the bifurcations, there is another way of looking at it, which would be by starting with x dot equal to f of r and x, and systematically looking at this Taylor series expansion over here and classifying systems with what vanishes and what doesn't, what are the first non-vanishing terms, play around, and as you play around, you can get, that's the systematic way of developing all possible bifurcations that a one-dimensional system may have. Yep. All right, so that's enough said on that. So let's end up this part of the discussion with purely one-dimensional systems with this very practical population dynamics example from Strogatz, which is worth doing because of the fact, number one, it's is a typical example of why these studies are useful. The phenomenon which was observed, that was essentially sudden outbreak of a particular insect. That was the phenomenon. The sudden outbreak meant a real large outbreak, led to, which in the 70s, I think, led to a large scale deforestation. Somewhere in Canada. So there was this somewhat unusual phenomenon that there was a large-scale deforestation over a period of 2 or 3 decades, and I think a couple of decades. And when people looked at it and tried to, it was caused by the sudden tremendous increase in the number of some particular kind of worms, which were bad for the foliage. So the point was that can I set up a model for this kind of a system, which would give me some control of what to do in future. So why set up a model for, the point is that if you have a working model with a couple of parameters maybe, then it is possible that you can, if there is a question of initial outbreak, you can vary the parameters and stop the phenomenon before it spreads too far. So, all right. The point is, what kind of a model to take? Now, what kind of a model to worry about is so that number one is that you see there is this question of insect population. Let's say insect, the number which is n of t. So now is that question number one, is that the only dynamics? But certainly there would be dynamics associated with the insects obviously feed on the plant leaves and so on and so forth. So there would be a dynamics associated with the leaves, etc., on which they feed. And it's consequently going to look like a rather complicated problem. This is where what we talked about in the very first day, something which always is going to be a big help, is the question of separating time scales. The insect population grows in a space of months. So the time period that you associate with the change in the insect population is days to months. The dynamics associated with the leaves, the sort of being affected by the insects and so on and so forth is a question over a year. So the time scales of how this population changes and how the dynamics associated with the leaves is going to affect the population dynamics of the insects. That is not, the dynamics of the leaves is not going to, this is a slow dynamics which is not going to affect the fast dynamics of those. For all practical purposes, so far as the insects are concerned, their growth and their birth and death is independent of what kind of nutrition it can receive from the leaves. So in that situation, it is this n dot is a logistic model that if there was an unlimited supply of foliage, then they would simply grow. But given the fact that there is a limited amount of foliage, they would eventually have to saturate. So there is this question of killing off, and so it is you stop the indefinite growth by this essentially killing off term. Pairwise interaction kills off things, and so it's some kind of a minus beta n square. So that's what generally is called the logistic equation. And obviously this is, as you can see, just the transcritical dynamics that I had. But now these are insects, so they have another death rate. That has to do with the question of birds. So birds reduce the insect population, and that's something which one has to worry about. So that's where the whole, actually this modeling business, this is where one has to pay heed. If you said the large and small time scales are unaffected by the foliage and so on and so forth, so I write down a logistic equation, you stop over here, and that's the end of it, you get nothing. But then you do realize, and this is where that what could be an important effect in this equation is the fact that birds, as soon as the birds will see worms sitting around, they are going to eat the worms, and that's going to deplete the number of worms. So this is where the additional term, so there is minus some P of n, which is effect of the prey. Effect of the prey on diminishing. So now what kind of a P of n? The whole point over here is a question of mixing maths, which is really at a trivial level, with some intuition which is the thing which seems to work very well. So a judicious mix of nice intuition and simple maths. So that's what makes it interesting. So you now have to know what kind of P of n am I going to get. This is where, I mean, when it is small, if n is small, P of n proportional to what? P of n proportional to what? The normal tendency would be to say that P of n would be proportional to n, the larger number of, if it's a small number, so I mean if you have 5 and you have a certain growth rate that if birds eat them up, so if it's 5 you eat them up in a fashion at a fraction which would be the same if it is 10, and so small numbers, I mean where the rate should remain the same, and it's therefore the rate at which they are eating is proportional. You would certainly eat them at a rate with which they are growing. This is where the insight was that it would not be true in this forest that if I have a small number of worms, then the worms would be hidden in the foliage, and therefore it would be difficult for the birds to pick them out and eat, and therefore the PFN going as n is much too a higher rate for so n is some reduced units, n goes from 0 to 1, let's say. So in the question of it being proportional to n is not a good thing. It would be some smaller power, and the next smaller power which still maintains an analyticity is n squared. So if n is small, the point made was that the expectation that you would have, which is n, would be diminished to n squared because small number of insects can keep themselves hidden and therefore shield themselves better from the prey. If n is large, then of course, I mean, this fails, and the population, I mean, the birds just come and eat them at a constant rate, and therefore, if n is very big, n large, P of n would go to some constant, let's say a. So you model P of n by an squared divided by some b plus n squared. So that if n is small, it's proportional to n squared, which is an squared. And if n becomes very big, then it is the rate Pn, sorry, this should have been Pn equal to A. It's a constant, diminishing at a constant rate. So n becoming large, this term dominates, this goes away, and Pn is equal to A. So here is this functional form. In a small n, an squared over b, large n goes to a, and therefore you propose that n dot is equal to Rn minus beta n squared minus a n squared. Let's put a square here. So this was the model that
so would you kindly repeat that how pairwise interaction decreases population?
Pardon?
That beta n squared term minus
this beta over here.
Yeah.
That's a question of, so I have nothing but if I have an unlimited amount of food available, then it is just an exponential growth which is n dot equal to Rn. But if I have a limited amount of food available, which would be what is available on a particular branch or whatever, then after a while you would be competing the insects that you have would be competing with each other for this share over here. Competing means that they kill off each other, and that's the killing of how many pairs, pairwise interaction kills them off, so it is something which is proportional to it. So this part over here is what is known as a logistic equation, often used as a model for fisheries and so on, as you would see in the Stogat's problems. So minus this P of n, and this was the model that, now what does this model do for you? If I scale n by b, so let's say I write n over b equal to some small n, then n dot is equal to Rn and minus b beta n squared minus a n squared over 1 plus n squared, right? Now I can do another rescaling. So this is, I want to take the a out of there. So it is n 1 over a dn dt equals r over a n minus b beta over a n squared minus n squared over 1 plus n squared. I do a rescaling of the time. So a dt is equal to some d tau. So as time rescaling, call r over a some r bar, and this b, this is this coefficient which is another constant, this group b beta times a, this is going to be some new number has to be introduced, and let's call it r bar divided by k. So I'm calling r over a equals some r bar, and then there is an independent coefficient over here which I'm calling r bar over k. So there are two independent parameters, r bar and k, and I'm going to replace n by x to make things look like x dot equal to f of x, and tau when there is no cause for confusion, tau and t I will so happily swipe. So x dot, and once again who writes r bar, so you write r, and then it is x into 1 minus x over k minus x squared. So that's this is a particular non-dimensionalization. I could have done the non-dimensionalization in very many ways. It is simply, all that this is telling you, that there are two parameters which would have to be left in this system. Oh, right now, looking at this over here, it seems there are 4 of them. 4 are overkill. So I have done one particular rescaling to show that 2 of them are what needs to survive. And so that's what the story is. I could have done with different parameterization of this, different rescaling, and then it would be maybe two other constants sitting somewhere else, different from where I have put them. Good. So x dot equal to, so this is what the dynamical system looks like at the end of the day. So first thing is fixed points. Obvious fixed point, x star equal to 0. Not so obvious fixed points, r into 1 minus x star over k is equal to x star over 1 plus x star squared. So, so there are 4 fixed points. It's a quartic which you would have to solve. And one of them, is trivial. There is x star equal to 0. And then it reduces to cubic, which would be solvable too, but it's a little more hairy than, because over here the cubic term also has, the cubic equation also has a squared term, which is the first thing that you need to remove. Cubics are easy to solve if they are in the form y cubed plus ay plus b equal to 0. They are nasty but solvable if it is z cubed plus az squared plus bz plus c equal to 0, because over here now the first step has to be to translate z and remove this term over here to make it look like this. But when you make it look like that, the a and b start looking clumsy, and so on and so forth. So not a good proposition. What I'm after is that solving that cubic, although doable, is not a good proposition. So you can take recourse to solving it graphically. So you solve it graphically with only need the, so this is x star over 1 plus x star squared. That is going to look like, that's going to rise linearly, go up to, so this is a function of x star, and it is the two functions x star over 1. So it starts linearly, goes up, and then drops to 0. Something like this, slow drop to 0 as 1 over x.
So you're drawing just that function or the
I'm drawing, so I'm trying to solve for x star from over here, right? So I'm drawing the right hand side and I'll draw the left hand side, right? And look for the intersections. So this is my, and then there is the other is a straight line which will go to 0 at x star equal to k. So it will go to 0 at x star equal to k, and it will have at x star equal to 0, it has a value of r. So it is going to be, so it's going to be r over here. So r, which can be here, here, or here. So let's say it's r and it's sitting over here. And it is going to, depending on where your k is, suppose k is over here and r is over here, then this is r and this is k. So this is what it looks like, and you have one fixed point. So there is going to be one fixed point which is going to, so in that situation there are two fixed points in this problem. Obviously there is a fixed point sitting at x star equal to 0 which we are not seeing, and but then there is, from the intersection of those two, there in this particular figure, that picture that I have drawn, it's one. But now imagine that the k is large enough and k is somewhere over here. So this is where k is. And I can, and let's say my r is somewhere over here, and if I try to, let's backtrack and draw this a bit. So here is another possibility. Here is r sitting over here, and k is sitting over here. So in this white, I had pegged k over here, and I had pegged r over here. And what you found was that there was just one intersection. Here I have pegged k over here and pegged r over here, and there are three intersections. One, if I keep r fixed and rotate and change k. So I want to keep r fixed and change k by bringing it in. Then these two fixed points so I keep r fixed and change k. These two fixed points are going to move closer to each other, and eventually there will be a tangent bifurcation over here, because there would be a particular value of k for which this line will become a tangent. And thereafter, there can be only, those two fixed points have disappeared, and if I change k any further, there is just one. Alright? Now, so I can have two fixed points, or I can have one. I always have. So there is a question of having either three fixed points or one fixed point, and at one particular k value over here, I have one fixed point and another which is a sort of semi-stable point, which we saw happens when these two actually just merge. So you are going to change from two fixed points to four fixed points, or vice versa, and you can go from one to other or this with changing k. Alright, so now let's look at the stability of the fixed points. Suppose I ask the question, is this fixed point over here stable or unstable, what would your reaction be? I mean, I'm asking the question about this fixed point, whether this fixed point is going to be stable or unstable. So I'm asking about the last one over here, the one at the largest value of x star, this particular fixed point. Do you think it's stable or unstable? Stable, right? So that's because the origin is always unstable. So this is, if r is greater than 0, the origin is completely determined by x dot equal to rx. So the origin has to be an unstable fixed point. So the origin is unstable, therefore this is the next chap, and this one is going, so they have to go in a sequence in this 1D problem. Unstable, stable, over here it is stable, unstable, stable. So what's to be noted? What's to be noted is that this is a very large value. The two fixed points which are stable are one at a very small value of x star, which is sitting somewhere over here, and the other is at a very large value of x star. So this is the population, this stable fixed point is the subcritical value so far as destroying trees are concerned. And this is the outbreak, the insect outbreak, which is the problematic business. Now, what's your control? What's your control is that y setup. So this is the basically the story, that this kind of a model that we have set up over there can give me a very large, can give me a fixed point, stable fixed point at an unusually large value of the number of insects. So it's normally the stable fixed point is hovering somewhere over here. As you can imagine, that this curve over here, x star and 1 plus x star, has a maximum value at this maximum of this curve is at 1 over 1 plus x squared minus 2x squared over 1 plus x squared whole square, that equal to 0, so x equal to 1. So x equal to 1 is where the maximum value is. So this is 1. So in these units, the normal behavior is that the fixed point, stable fixed point, is at a value which is lower than 1. But if something happens, then it is going to be that you can find yourself looking at a stable fixed point for this number, which is at an unusually high value. So that was the big thing about it, which was nice, that it showed that it is possible by controlling parameters to actually get things going over here, so that you could predict that given a value of r, given a value of r, which sort of you can get from good days when there is no question of outbreak or anything. You look at the logistic equation controlled situation, and you can get a that is, look at the situation in an isolated environment without birds. You can sort of get a feel for what this the factors R and K so this is what the factors R of R and K are in insect population which is not affected by the praise at all. So in a closed environment, you can get some picture of R and K. And then you can see that if what these R and Ks, if what's the game that you would have to play so that the R and Ks don't get out of hand in a manner that you reach the tangency condition over here. So this tangency condition is the critical business, that if you become tangent at this point, thereafter if you tilt the K a little more, keeping R fixed, that's when you are going to get this stable fixed point, and therefore this tangency condition, the value of R and K which you get at this tangency point is important control on this problem, where if you keep things on the side of R and K where you don't have this problem with 3 fixed points, then you are going to be safe. So the point is that, all right, what would be what is it that one needs to calculate? Thereafter, I mean, it's all going to be pretty straightforward. We will not go through the details, but let me just finish by showing the fill in the blanks, which you can very easily do. So I want to know, it's a tangency point which is vital. So that tangency point, point over there, that is this straight line over here, has become a tangent to this curve at the point where they intersect. So the intersection point, of course, is determined by that, and the tangency point is going to be determined by the slopes becoming equal. The slope for the straight line, slope of straight line is minus R over K. So slope of the straight line is minus R over K, and the slope of this x star over 1 plus x star, that slope is going to be given by, it is 1 over 1 plus x star square minus 2 x star whole square, which is equal to 1 minus x star square plus 1 plus x whole square. So that's the slope over there. So the slope is going to be, so it is minus R over K equal to 1 minus x star square over 1 plus x star square, 1 plus x
squared whole square.
Right? And so this has to be satisfied simultaneously with the fact that x star over 1 plus x star equals R into 1 minus x star over K.
So 1 plus x square.
Huh?
1 plus x square in the denominator. Last.
Okay, thank you. Yeah. So that's your. So these two have to be simultaneously satisfied, which means that I have to sort of. All right. Let me just go one more step. So eliminating x star from over here is going to give you a relation between r and k, and the point would be that if I want to look at what is the x star value over here, then what I need to do is write minus r over k is equal to, this is 1 minus x star square divided by 1 plus x star square, which can be written as x star square. So 1 plus x star whole square is equal to x star square divided by 1 minus x star over k whole square. So this is 1 plus x star whole square is x star divided by r square over here. So it is x star square divided by this, so it is r square over here into 1 minus, what did I do? It's a question of 1 minus r square, but it didn't get it. So it's r1 minus x star into r square. What am I after? I want to divide out by, after squaring, I want to divide out these, so it is, let's see, I want to square and divide out, so it is minus r over k on this side divided by r square into 1 minus x star k over whole square. That is equal to, divide out on this side, it is 1 minus x star square divided by x star square. Right? So this is it. So which is equation for x star. This, from here you get x star square as a function of r and k, and then you can come back and put it back over here, x star square in terms of, and that gives you the whole business. So there is a little bit of algebra which you can essentially do and get the tangency condition out. So from here you get the tangency point in terms of r and k. Once you have the tangency point, you know what is the relation. You have the two tangency conditions, and that gives you the way of getting the respective values of the relation between r and k. So here we are. So that's what should it be? What are you looking, eventually what do you want to do? You want to write, you want to put this in the RK plane. So this is two parameter problem. It is R and K plane over here, and it is just like the magnetization problem that we did last time, that there was this question of the RH plane. Over here, similarly, it is a question of the RK plane, and what should I have in the RK plane? The RK plane would have a region where I have two fixed points, and a region where I have 4 fixed points, and there should be, what you are supposed to do is find the boundaries in do this algebra to find the boundary of in the RK plane, so that there are 4 fixed points on one side and there are 2 fixed points on the other side. So it is this boundary curve in the RK plane which separates out the 4 fixed points from the 2 fixed points, which is of importance. And that boundary over here, that relation between R and K, which you get by putting in the value of x star over there, is the interesting business which tells you how to control. What you don't want to do is you don't want to get into this region where there are 4 fixed points, because that would automatically tell you that there is going to be a stable fixed point with large number of insects. So calculating this R versus K boundary is actually of practical interest and could be a way of at least controlling this particular kind of insect outbreak. So this is why simple calculations can give you answers which can be put into practical use, and this is where the first order systems are coming very handy. So the primary business is population dynamics. That's what the first order systems are very good at. As we saw that sometimes you can force things, the magnetization mean field picture can be forced into a one-dimensional system, so can the pumping of the laser be cast in that form. So for the population dynamics, it's natural. For the other connections, it's a bit forced. You do this and that and a little bit of approximation here and there and make the first order. But this is about it. Just x dot equal to f of x. This is about all that one can say. The next thing I'll stick to one more lecture on one-dimensional system, but the variable is going to be something which is, instead of x, would be theta, and we want to talk about theta equal to f of theta. And it is a one-dimensional thing, but you have the situation that theta can repeat itself. So theta is between 0 and 2 pi, so every time it goes past 2 pi, it repeats. So while a first order differential equation, which we talked about, x dot equal to f of x, cannot have anything other than a fixed point, the theta dot equal to f of theta can give you periodic solutions just because theta can go and repeat itself. So that's why theta dot equal to f of theta forms a slightly different, is a slightly different kettle of fish. So the next lecture would be on that before we pass on to real two-dimensional systems. Now, what I need to tell you that this next 2 weeks of this semester is is a large disruption when it's Allahabad. So it's unfortunately in the week of the next week, which starts on 18th, and the subsequent week, which starts on the 25th. I have to be away on Wednesday and Tuesday to Thursday on both these cases, which leaves me with essentially no class days. So if it is all right with you, on these 2 weeks I would like to take at least one lecture on Saturday over here and Saturday over here, which would be, let's say, at 11 on both days, if that's a suitable time, or if it is not, you can tell me what suitable time is. But for the week of 18th and 25th, I have the problem in the middle of the week, a one-day problem which escalates into 3 days for here. So this will have to, whatever is, if 11 is my suggestion, if you want any other time, it's fine with me, whether earlier or later or what have you. But then from February onwards, it's smooth with hopefully no.
So this curve that you drawn in the RK plane,
Huh.
4.2, that will be a closed curve. Now
No, it won't be a closed curve.
But for large enough curve, we see that we can only get 2 fixed points. Means in this diagram, if we see that to large
Yeah.
enough curve.
Yeah. But that wouldn't close it would put a limit on this side. You wouldn't get a yeah, you're right that it's not that I go through infinity. Yeah. So yeah. So that's the scheme. I mean, for this month of January, just bear with me. I mean, February.